So we are going to discuss the idea of acid-base neutralization reactions, which is going to lead us into a new technique called titration. So if you remember from our acid-base equilibrium, if you take an acid like HCl and react it with a base like sodium hydroxide, you are going to create water and, in this case, sodium chloride salt. So you always have water being created from a neutralization reaction, and you have some sort of salt. So whether or not we're using chloride or nitrate, or we're using sodium or calcium, you always wind up with a neutralization reaction product of water and some sort of salt. So for example, if I use calcium hydroxide and I use phosphoric acid, okay, even though this is weak, when you do a neutralization reaction, eventually all the H's get pulled off. We can write a neutralization reaction that shows that I've created water, but now I've got to make sure that I balance it. And I've created calcium phosphate. Okay, so don't forget you have to balance. So I've got 2 hydroxides here, I've got 3 hydrogens here. That's not going to give me just 1 water molecule. So I've got to write a balanced equation. 3, 2, 3, and then I should be good to go. Okay, so I'm going to create 3 water molecules, no, 6, whoopsie, 6 water molecules as a result of that reaction. So a neutralization reaction, regardless of how many you get, you're always going to create water and some sort of ionic substance. Now let's talk about number-wise. The big idea here is that you have to have the same number of H pluses and OH minuses in order to neutralize the reaction. That's the big idea. So it didn't matter what we made over here. I had to have equal amounts of H plus and OH minus in order to make my waters. So when you do a neutralization reaction, this is really the reaction that matters. And in order to have it completely neutral, we need to make sure that none of these are in excess. So really what we're saying is that we want the moles of H plus to equal the moles of OH minus when this reaction is finished. So that gets us to the ideas that are on the organizer. So page 1107, if you haven't pulled that out yet, make sure you do that. But that's the idea that we're going to take a look at. You've got the moles of H plus have to equal the moles of OH minus. Now this should look a little familiar because when we did dilutions, we came up with the same idea. The moles before have to equal the moles after. And if you remember with that dilution equation, we used concentration times volume equals concentration times volume to mathematically calculate that. If you look at the neutralization reaction, or the neutralization equation, we've got that same idea. Concentration times volume equals concentration times volume. The only other thing you have to add, and it's not coming in very clearly, the only other thing you have to add is how many H pluses are in the acid and how many OH minuses are in the base. Because it's not the molarity of the compound, it's the molarity of the H plus that you're really worried about. And likewise, it's not molarity of base, it's molarity of OH minus, because the moles of H plus and the OH minus have to be equal. Okay, so here's a quick example. You've got a solution with sulfuric acid and aluminum hydroxide that you are titrating. So you measure out 10.65 milliliters of 0.1 molar sulfuric acid. You want to figure out what the concentration of the aluminum hydroxide is. And you find that when you titrate it, and we'll talk about what titration is momentarily, when you titrate it, you find that it took 14.95 milliliters of the aluminum hydroxide to neutralize the base. So when you look at the equation, I'm going to zoom in a little bit because it's zooming a little fuzzy. When you look at the equation, here's the original, number of H plus, I know that, it's 2. Molarity of the acid, I know that. Volume of the acid, I know that. OH minuses, I know it's 3 because I'm using aluminum hydroxide. The molarity is what I don't know, but I do know how much volume I used. So what am I doing? I'm really trying to figure out what's the volume of the base. So I've got 2 H pluses from the sulfuric acid times the molarity times the volume. And just like in dilution, I don't actually have to make the volumes liters. As long as both of them are milliliters, unit-wise, they'll cancel out. I'm going to divide that by 3 moles of hydroxide and 14.95 milliliters of aluminum hydroxide. So what do I wind up with? I wind up with a molarity that's 0.04749. So it's as simple as that. Now, this is an example of a complete titration. We'll talk about incomplete titrations in another video. So every time you do a neutralization reaction, every time you do a complete titration problem, you wind up with a pH of 7 because of the neutral solution. Okay, so here's a second one. Go ahead and take a moment and work your way through that. You've got barium hydroxide and hydrochloric acid. Can you tell me what the molarity of the acid is going to be in this case? So pause the video and see if you can work it out. If you have come back now, you've got the number of OH minuses times the molarity of barium hydroxide times the volume of barium hydroxide, all divided by the fact that you have 1 H plus, in this case we had 2, the numbers of H plus, 1 H plus times the volume of the acid was the 49.21, volume of the HCl, and we're trying to figure out what the molarity of the acid was. So if we plug in those numbers, I'm running out of space, so I'm getting 2 OH minuses for the number of OH minuses. The molarity is 0.325 molar, and I have 25.98 milliliters, all divided by the fact that I have 1 H plus and a volume of 49.21 milliliters. So if I do my math, I wind up with a molarity of 0.343 molar for the barium for the HCl. And that hopefully makes sense because you have less milliliters of barium hydroxide involved than you do HCl. And so it would make sense because barium hydroxide has 2 OHs. So for every 1 milliliter of base, you're delivering 2 moles of OH minus. So it makes sense that it's going to take more HCl to equal that out. So there's the idea of titration equations. What I want to do now is I want to go on and talk about the actual process of titration. So I'm going to, excuse me, escape from here for now and go to this simulation. It is out of the University of Oregon, and it's actually quite nice. What you are seeing is a setup for a titration equation, or for a titration. So you've got acid and base. We're going to do strong acid, strong base this year. We're not going to worry about anything weak, but you're going to put one of them in the burette. So I'm going to do a strong acid, strong base. I'm going to put the base in the burette. I'm going to put the base in the burette, and then I'm going to select that I want to use. We're going to keep it simple. I'm going to use HCl and sodium hydroxide, something that we're so used to using. And I need to put an indicator. So in this case, the indicator is going to be phenolphthalein. That's what you use when you get a strong acid, strong base titration, because you get that neutral pH of 7. All right, so let's take a look at what's involved. I'm going to scroll down just a little bit. So in my flask, I have HCl. I know what its molarity is. I know how much volume I have in here. I have it on a stir plate. Notice that this little thing spinning, that's a magnet. And we actually have hot plates that are also stir plates, so we could do this in the lab. Unfortunately, we can't this year. But the stir bar is rotating to try and keep the reaction mixing so that it completes itself quick. What I'm going to do is I have filled this burette up with base. So I'm going to slowly add base to this, excuse me, until I know that the neutralization has finished. Now, phenolphthalein is an indicator that will change from colorless in acid solution to pink in blue solution. So what you're going to do is what I'm going to do is I'm going to slowly add sodium hydroxide. I'm going to start by sliding this up and adding it a milliliter at a time. So notice I have 25 mLs of acid in a 0.211 molar solution. So I'm going to slowly start adding acid. So you can see the volume keep going up. It looks like nothing's happening. That's because in here there is so much more acid than there is base that the indicator is still going to stay colorless. Only when I start to get an accumulation of base will you start to see a color change. And that's actually what we're looking for. So let's see if I can do it slowly enough. I'm going to add it 1 milliliter at a time. So this could be a little boring for the time being. It's much more exciting when you actually get to do it yourself with your own hands. But I'm looking for the point where I'm starting to see the pink color form. And then, oh, there it was. Did you see that? So now I'm going to slow down a little bit. So look at the flask. Maybe I'll add just a half milliliter at a time. I can't get it to do that. I don't want to overshoot. I overshot. Look what happened. See how bright pink it got? I overshot. I don't know if I can take any out or not. Maybe I can't. All right, so we're going to reset this. That's what happens if you overshoot. If you add too much base, it gets really bright pink and you've missed the end point. The point where you've just neutralized all the acid with the base is called the end point. So here's my concentration and my volume once again. Still going to use phenolphthalein. So I'm going to add the acid, again, a little slowly or a little quickly until I start to see the pink color appear. I played with this earlier, and it's actually a little tricky to not overshoot, but then to not have it take forever. Okay, so now I'm going to go to dropwise. I'm not going to risk it because I don't want to waste your time. So dropwise, I'm going to add base. Notice that it's going in just drop by drop. The pink color is still there, but it's not there permanently. What I'm looking for is just the faintest pink color to stay. That's when I know that I've reached my endpoint. And this is the trick when you're in lab physically doing it yourself. Oh, there it is. There it is. I added one too many drops, so I actually am going to go back to 9.02 to do that calculation. So on my calculator, you can't see me doing it. I guess I could bring it up. This guy. So on my calculator, I'm going to do, I've got 0.1655 molar of HCl, and I have 25 milliliters of it, and I know I only have 1 H+. Well, I need to figure out the molarity. That's my unknown, and I used 19.4, I'm going to take it back down to 2 milliliters because I added that extra drop by accident. 19.42 milliliters, and again, it's OH minus is just 1 because it's sodium hydroxide. So if I do that math, I wind up calculating, turn my calculator on would be useful. I wind up with a molarity that is 0.2130 molar. So now I could take that number and plug it into the molarity here, 0.213, well, I guess technically 1 on my calculator. So I'm going to 4 digits since everything else is 4 digits. I'm going to click OK, and hey, look, they said that I was right. I got the concentration correctly. Okay, so now on my graph, what I can show you, one last thing, I can show you that I had a lot of acid in the flask to start with. So as I added base, the pH changed really slowly because the acid was overwhelming it. But as more and more base got added, the pH started to change more quickly. And eventually I reach a point where one drop takes it from here up to here. So this middle point is called my end point. That's how I know that I'm done with the reaction. And then once if I keep adding more base, then it's going to become basic, but it's also going to kind of flatten out. So that's how you do a titration. The titrant is going to be typically the acid. The burette is going to hold the base, and so you're going to add burette to the acid in the flask. An indicator, typically we use phenolphthalein, is going to tell you when you're at your endpoint. So there's the technique. Unfortunately, you don't get a chance to do it for real. However, I am going to give you a set of lab data to let you practice this whole idea of titration. If you would like to play around with this simulation, I've actually linked it to Schoology. There's a link on Schoology that gets you to this simulation page. It does require Adobe Flash, so you would need to use it on a computer where you could open up Flash and download it. But it's a pretty fun simulation. All right.